At the end of this course and also at the end of Physics 122, I like to take a brief look at what physicists usually call modern physics. I kind of think maybe modern doesn't mean the same thing to physicists it does to other people, because this stuff is over 100 years old. But compared to Newtonian mechanics, which is 300 years old, I guess it's relatively modern. Anyhow, it turns out that in the early part of the 20th century, some of the basic assumptions on which traditional physics is built had to be re-examined. Particularly sadistic physics teachers I have heard have been known to walk in one day and say, you know, that stuff you've been struggling so hard to learn all semester long, well, it's all wrong. Blah. Well, you know, that's not really true. It's not all wrong. Newtonian mechanics turns out to be another one of those approximation schemes, kind of like frictionless surfaces and ideal gases and things like that. It works very well under certain circumstances. And in those circumstances where it works, it's simpler than the more all-encompassing model. And so, you know, Newtonian mechanics successfully built the Brooklyn Bridge and got people to the moon. And basically, when it works, is if you're not moving at speeds that are close to the speed of light, and if you're not talking about things that are the size of atoms and molecules or smaller. And that's almost everything you encounter in everyday life. But the story of the special theory of relativity usually begins with the Michelson-Morley experiment, which I'm not going to take the time to explain to you. If you're interested, I'll refer you to not only our textbook, but basically any textbook. It's an experiment that was done in 1887, I think. Don't quote me on the date, but I think that was it. And the unexpected result is that the speed of light appears to be a universal constant, okay? It's alongside of things like the gas law constant and the gravitation constant and that handful of numbers that describes how our universe is put together. The speed of light is the same to all observers, no matter what they're doing, no matter where they are or when they are, so far as we know. So this was unexpected. Isaac Newton took space and time to be absolute, okay? If 1 minute passes here on Earth, 1 minute passes on Mars, and so forth. To Newtonian mechanics, speed is relative. If you are, for example, riding in the back of a pickup truck, which, yeah, that's illegal these days, but just as sort of a hypothetical thought experiment. We're going to say the pickup truck is only going 20 miles an hour anyhow. And you've got a baseball and you see your friend standing by the side of the road and you throw the baseball to your friend. Well, let's make the pickup truck going, no, that's right, 20 miles an hour for the pickup truck. You throw the baseball at 30 miles an hour relative to you. Your friend on the side of the road catches a baseball that's going 50 miles an hour because you threw it, you know, the speed of the truck gets added to the speed that you threw it with. 30 miles an hour relative to you, 50 miles an hour relative to your friend on the side of the road. Well, that's how it works at, you know, a handful of, actually not just at low speeds like you can throw a baseball. That's how it works for example, any spacecraft that's ever been built, things that are going tens of thousands of miles an hour. That's still how it works. But if you start getting close to the speed of light, which is really fast, things get more complicated. As for the speed of light itself, if you're on a spaceship going 200 million meters per second, and you've got a laser pointer that you shine on your friend who's standing there on the Earth, and the speed of that light as it leaves your laser pointer is 300 million meters per second. What does your friend there on the Earth measure for the speed of light in that beam? 300 million meters per second. It's as if you threw that baseball off the pickup truck at 30 miles an hour, and your friend caught a baseball that was going 30 miles an hour, not 50. Things get kind of counterintuitive when you get into modern physics, but not only is this supported by other experiments, aside from the Michelson-Morley experiment, other things that have been done more recently, but Albert Einstein, while he was probably aware of the Michelson-Morley experiment, he was more interested in things from the theoretical side. And the thing that bothered him was that Newton's theory of mechanics and Maxwell's theory of electromagnetism were inconsistent with each other in some ways. And he wanted to iron out the wrinkles, okay? So from the theoretical side, he came up with something that was consistent with these unexplained experimental results also. So the underlying thing here is that since speed is distance over time, if the speed of light is not relative, relativity is about relative motion, okay? In the back of the pickup truck, I'm in one frame of reference. On the side of the road, you're in another frame of reference, and we're in motion relative to each other. I'm moving 20 miles an hour relative to you. If the speed of light is not relative, okay, if it's not different in different frames of reference, then it must be that distance and time are relative instead. So let me illustrate that with a hypothetical experiment that would be a little more difficult to actually do than just throwing a baseball from the back of a pickup truck. And let me mention again that even though I like to talk about spaceships in this part of the course, because I think it's kind of nice to picture a situation you could actually, picture yourself experiencing. Not only does no existing technology get a vehicle going fast enough for these sorts of things to happen, but even any imaginable technology, which doesn't mean 1,000 years from now somebody won't come up with something we can't imagine now, but you need to be going to 3-digit accuracy, something like 10% of the speed of light for these types of effects to become noticeable. Where they are a very everyday routine kind of thing is if you're talking about elementary particles. Things like electrons are very lightweight, and it's not hard at all to get them going extremely close to the speed of light. And relativistic effects are routinely observed in the high energy physics laboratories that are scattered around the world, and other situations like you can get in astrophysics where elementary particles get whipped up to very, very high energies. But for a vehicle a human being could ride in to go this fast is science fiction for the foreseeable future. But I figured I'd make it a spaceship because you can't really picture yourself riding on an electron. Anyhow, let's say I'm in spaceship A and you're in spaceship B. And this is somewhere out in, deep space, far away from any stars or planets or anything to complicate the story. And well, from my point of view, you go flying past me at a very high speed. As far as I'm concerned, I'm at rest, and you're zipping past me at close to the speed of light. Of course, to you, it looks like it's the other way around. You perceive yourself as being at rest, and you see me flying past you at a high speed in the other direction. Now, which one of us is really moving? Oh, well, you see, that's the thing. There isn't any way to tell. Um, if you're in the car going down the thruway and it looks to you like all the trees and houses and things, you're heading toward the east and it looks like all the trees and houses are headed toward the west. Well, you have this psychological thing going on that says you know that the trees and houses are anchored to the earth. It's really you that's moving. But if you're out in space, many light years from any planets or anything, how do you tell which one of you is really moving? And for that matter, even if you are close to a planet is just a really big spaceship. How do you tell if it's sitting still or moving? The answer is that there is no answer. So my point of view is equally valid to your point of view. There is no experiment that can be done to determine which one of us is really moving. And I should mention, by the way, that we're moving with a constant velocity, okay? The thing that's special, oh, that's disappeared off the top here. The thing that's special about special relativity is that it's a special case. We're only considering non-accelerated motion. If one of your spaceships is going to accelerate, that gets you into the general theory of relativity, which Einstein published 11 years later. No, 10 or 11, depending on how you want to look at it. Special relativity is from 1905. General relativity was right at the end of 1915. I think it was 1916 by the time he got it published. Anyhow, we're both moving at a constant velocity. I think you're in motion. You think I'm in motion. Over here to the side is some sort of a device which is at rest relative to me. So from your frame of reference, it's zipping off to the left with a speed v, just like I am, okay? To me, it's at rest. On this device is some sort of a light detector. And when that detector detects a burst of light, some sort of observable thing will happen, like maybe there's a little flag on the device that'll start to wave or something like that. Anyhow, just as we pass each other, right in between us is a flash bulb like you might have on a camera, except with a camera, there's a reflector behind it to throw all the light in one direction. And this is just a light bulb that's out in the open. So it creates a bubble of light after it flashes. As time goes by, this bubble of light expands about the point that it came from, traveling at the speed of light in all directions. So what does this look like, first of all, from my frame of reference? Well, to me, this flash bulb is more or less where I was at this motion. It was right outside my window, just like, because we pass each other really closely, okay? So this flash bulb is maybe 20 feet outside the window of my spaceship when it goes off. For all practical purposes, I am at the source of this bubble of light. So a short time later, a time interval delta t, the bulb will have the light from the bulb will have traveled the same distance in all directions, traveling at the speed of light. Um, the symbol we usually use for the speed of light is c, as opposed to v, which is, we don't want to call both speeds v, that would get confusing. So v for velocity, that's, as far as I'm concerned, that's the speed of your spaceship. And since we've already used v for that, we'll use c for the speed of light in a vacuum to be precise. The amount of time that passes between this picture and that picture, as measured by me, okay, frame of reference A, that's delta t A. Distance equals speed times time, meters per second times seconds equals meters. So this sphere has a radius of d when it reaches the light detector. So after this time interval, delta t, the light hits the detector and the little flag waves. Now, what does it look like from your frame of reference? Well, to you, the flash bulb is right outside your window, like 20 feet outside your window. And so for all practical purposes, you are at the point that this bubble of light expands around. Doesn't matter whether the flash bulb is moving relative to you or moving relative to me. The relevant thing is just that it was, at the moment it flashed, it was located right there, okay? So you're at the center of this expanding bubble of light after, when it reaches the light detector, after a time interval that's delta t b in your frame of reference. Well, here's where we're getting to the point of the whole thing. As the bubble of light expanded, the light detector was moving. It was running away from the point where the flash bulb flashed. So by the time the light catches up with it, the light has to cover a greater distance than in this other frame of reference where the detector was at rest, okay? You can see the way I've drawn it, that this distance that the light travels here is greater than the distance it travels in my frame of reference. This, once again, is d, but there's an x component also in this case. So c times delta t b is a greater distance, and delta t b is a greater time, because since the speed of light is the same to both of us, covering that greater distance at the same speed takes more time. So the point of the story is that we have here these two events. Event number one, the bulb flashes. Event number two, the light reaches the detector. These two events are separated by different amounts of space, fewer meters here, more meters here, and these two events are separated by more time, fewer seconds here, more seconds here. So different amounts of space, different amounts of time between the same two events, depending on which one of us we're looking at them. So space and time are not absolute, as Isaac Newton assumed. Space and time, distance and time are relative, different to different observers. So more time and distance between events where light has to catch up to the detector. The difference in the amount of time. Well, the way you go about deriving these equations here is by looking at a situation like I just was describing here. And, I'm not going to write it all out and do all that for you, but you can compare the distances. You got this triangle here, and you do the Pythagorean theorem, and there's a number of lines of algebra you'd have to go through. But when the smoke clears, the difference in the time intervals between two events is described by this equation. Oh, you can't see that. It's time for me to move it up. Time dilation. If you're watching a clock as it runs, the faster that clock is moving either toward you or away from you, doesn't matter which one, the faster the clock is moving, the slower it will go, okay? The 0 subscript here stands for the reference frame where the clock is at rest. 0 as in velocity equals 0. If you're watching the clock from a frame of reference where the clock is moving, the clock will run slower. The ratio between the two time intervals is represented by the Greek letter gamma, and gamma is equal to this, where v is the velocity of the clock and c is the speed of light in a vacuum. Okay. The usual, I mean, it's not that tricky to just throw numbers at a formula. Excuse me. The usual mistake that catches people is switching which frame of reference is which. So as with just about anything, it's a good idea to keep in mind what's supposed to be happening. Okay, keep the basic concept behind the equations in mind as you're working with them. The clock should look like it's running slower in the frame of reference where it's moving. Also, the distortion in length is called Lorentz-Fitzgerald contraction. L is the length as measured. This is the length along the direction of motion. Across the direction of motion, nothing changes. But things get shortened along the direction of motion. Okay, so L0 is the length as measured in the frame of reference where the thing is at rest. And L is the length when it's in motion. And once again, the amount of change is given by the same factor, gamma, that came up with the time dilation equation. So one more time, to keep straight which reference frame is which, in the moving frame, things get shorter along the direction of motion only, and time runs slower. And I think I mentioned this when we were further up the page, but for the 3-digit accuracy that we work to usually work to in a course like this one, you don't have to worry about relativistic effects until you get somewhere around, using a rounded off number, somewhere in the neighborhood of 10% of the speed of light. Now, if you're going to go more decimal places, then these things would matter at slower speeds. If you're going to try and measure something at, well, for example, relativistic effects have to be taken into account in GPS systems. Okay, both special relativistic effects, because the GPS satellites are in motion, and also the general theory of relativity comes in it, because at the altitude where the satellites are, Earth's gravitational field is a little weaker than it is at the surface. General relativity is the modern theory of gravity, Newton's inverse square law that we didn't actually cover in this course anyhow. But that's a weak field approximation to the more modern theory. But, think about it. You've got a satellite that's hundreds of miles, a system of satellites that's hundreds of miles above you, and it's trying to, based on the signals from the device you're holding, it's trying to figure out where you are to within an accuracy of a few feet. You don't get that level of accuracy from calculating things to 3 significant figures, okay? If they didn't take relativistic effects into account, they'd have you in the next town over after a day or two. Anyhow, so it's not like these things don't matter. It's just they don't matter if you're talking about a car driving down the road or something like that. But these are definitely effects that come up in, it's not all just, it's more than just philosophically significant, okay? These are issues that have to be dealt with in certain practical applications. Anyhow, I'll run through an example and then I'll have you try a similar one. So let's say that when it's sitting there in the Death Star, Darth Vader's spaceship is 10 meters long, like 33 or 34 feet, something like that. Well, he hops in the spaceship and goes roaring away. And pretty soon he's traveling at 99% of the speed of light. Well, you have some sort of a device that can measure how long the spaceship is off there at a distance. And also this part is a little different from the movies. We'll say that there's an enormous clock mounted on top of his spaceship, and you can watch the clock through a telescope. So as far as Darth Vader is concerned, this clock on top of his ship is keeping perfect time. But as you watch it through the telescope, how much time does it take the second hand to advance by 1 notch? Okay, so here's how that goes. Well, both of these things, Lorentz-Fitzgerald contraction and time dilation, they both depend on this factor gamma. So before I start on part A in particular, I might as well calculate gamma because I'm going to need that for both parts. By the way, I should point something out here. If you're talking about baseballs flying through the air or cars going down the road, or even things that you would think of as really fast, like a spaceship on its way to the moon going 25,000 miles an hour. Compared to the speed of light, 25,000 miles an hour is slow. I mean, really, really slow. So V over C is a small number. If you take a small number and square it, you get a really, really small number. And then if you take 1 and subtract a really, really small number, you more or less still have 1. And after you take the square root of it, it's going to be even closer to 1. So this is why you don't notice relativistic effects when you're throwing a baseball around or watching somebody go by in a car, okay? Distance and time as measured by somebody in that car is practically the same as it is to you standing on the side of the road, because at such low speeds, gamma equals 1 to more digits than you're going to care about unless you're designing a GPS system. But 99% of the speed of light, well, that's another matter entirely. Now, what I've noticed the average student tends to do is they go into their reference handout that I gave you, and they look up the speed of light in a vacuum, and they put that in for C. And then they calculate 99% of that, and they put it in for V. And this will give the correct answer. There's nothing wrong with doing that, except from a time management point of view. There is an easier way to get through the calculations. Instead of measuring speeds in meters per second, use the speed of light as your unit of speed. If you do that, V is equal to 0.99 times C, like it said in the question. Don't plug in anything for C, just keep calling it C. Notice that C over C drops out, and you just have to square 0.99, which is going to be easier than juggling these big numbers in scientific notation that you would have if you filled these in meters per second. So, little shortcut there you might want to keep in mind. Well, if anybody wants to see kind of an intermediate step in the arithmetic, after you square 0.99 and subtract it from 1, you'll have 0.0199. So you take the square root and then divide 1 by that, and it comes out a little more than 7. .09 is probably close enough, although I always like to carry an extra digit and then round off when I get to the answer. Part A. You look at the formula sheet, and it says L0 equals gamma times L. L0 is the rest length, the length the spaceship has when its velocity is 0. And the question tells us that that's 10 meters long. We've got the 7, a little over 7 for gamma. The length with the ship in motion is what we're looking for. So you just divide both sides by the 7.089. So as measured by you, the length of this ship that's rapidly moving away from you is just a little more than 1.4 meters. The faster it goes, the shorter it gets. Time dilation. About there, I guess. Part B. Delta T is what we're looking for. How much time passes in the frame where the clock is moving? The 0 subscript refers to the rest frame where the clock is at rest. So gamma is 7.089. 0.289. To an observer who is at rest relative to this clock, 1 second passes. How did I phrase that? Yeah. How much time for the clock to advance 1 second? So the second hand is in front of one mark. How much time until the second hand is in front of the next little mark? Well, if you're at rest relative to that clock, it will take the second hand 1 second to advance to the next second. But if you're watching through your telescope as this streaks away from you, rounding off a little bit, it's a little more than 7 seconds every time that second hand advances again. So that's just science fiction. Spaceships, as I said, don't go nearly that fast. The example I have for you on the top of the next page, on the other hand, is something real. It involves elementary particles called muons that were discovered back in the 1930s. And a muon, well, we aren't really going to get into the story of elementary particles in this class, but let's just say a muon belongs to the same basic family of particles that an electron does. They're both what are called leptons. So think of a muon as being a heavier version of an electron. It's negatively charged like an electron. The other difference, aside from being somewhat heavier than an electron, it's not nearly as heavy as a proton, but aside from its mass, probably the most significant difference is that muons are unstable. Electrons have an infinite lifetime. If there's an electron in that atom right there and nobody does anything to it, it'll still be an electron 1 billion years from now or 1 trillion years from now. Muons, on the other hand, undergo a process similar to the radioactive decay of a nucleus. And in just a few microseconds, they turn into something else, okay? Just like when a nucleus of carbon-14 turns into a nucleus of nitrogen-14 by giving off a beta particle. Now that's something we'll talk about right at the end of Physics 122. But in a process similar to radioactive decay, these things don't last. They've got a half-life of 2.2 microseconds. So muons are produced in the upper atmosphere in large numbers by cosmic rays. The Earth is continuously bombarded by high energy charged particles from space, protons and other broken up bits of atoms. The term cosmic ray is actually usually reserved for the really, really high energy stuff that comes from outside the solar system. I mean, there's a lot of ions that hit the Earth from the sun also, but the cosmic rays are the really high energy stuff. So as these cosmic rays collide with air molecules when they encounter our atmosphere, there's enough energy in the collision to create elementary particles, which, well, we won't get into the details of how that works. We'll just say it happens. That's where these muons come from. Okay, they are constantly night and day being created, and typically at an altitude of a number of miles, where the cosmic rays first start to encounter significantly dense air. even traveling very close to the speed of light, you can't get to sea level from up there in 2.2 microseconds, okay? In 2.2 microseconds, something going almost the speed of light can only go less than half a mile. If, distance equals speed times time. These things are being produced, 5, 6, 7, 8 miles above sea level, and yet they are in fact observed at sea level in, I guess, a minute before we get to that. They are observed at sea level in large numbers. So how do you explain that? Well, exactly how you would explain it depends on which frame of reference you want to look at it from. If you want to look at it from the Earth's frame of reference, it's time dilation. 2.2 microseconds is the lifetime of a muon when it's at rest. But these things are going close to the speed of light. Gamma is a big number, and it slows down their decay by enough that most of them reach sea level. So that's the one way of looking at it. The other way of looking at it is if you were in the muon's frame of reference, which would be a very bad idea, by the way, because it would mean that you're about to collide with the Earth at almost the speed of light. And the only good thing about that is that it would be over quickly. But if you imagine riding along with this muon as it goes streaking down toward the Earth, well, in that frame of reference, yeah, the muon only lives 2.2 microseconds on average. But as the Earth comes toward you, it's the Earth that's moving at almost the speed of light. And so it's Lorentz Fitzgerald contraction that makes the muons able to reach sea level, okay? Seen from that frame of reference, the Earth is not a sphere. The Earth is a pancake because it's contracted along the direction of motion, but not to the sides. And so the distance from where they're created to sea level is a lot less than that 5 or 6 or 7 miles that I mentioned. It's contracted enough that the muons can travel that short distance in just the 2.2 microseconds that they've got, okay? So, like I said a while ago, yeah, the stuff about spaceships is kind of science fiction-y, but you start talking about elementary particles, and there are plenty of real-world examples where relativistic effects are observable. So that's the background information for problem number 1. Pause it here and see if you can get those 2 numbers for answers. It's very similar to the one that I just went through. And here's the details. Those people who need them. Just like before, I'll start out by getting a value for gamma. One over the square root of 1 minus v over c, the speed of a typical muon, 0.998 times c. C being, again, the speed of light in the vacuum. V over c squared. C over c cancels out. Can't figure out where you went wrong in the arithmetic, here's some details. 0.998 squared is 0.996. Subtract that from 1. And 1 minus 0.9, or oops. Sorry about that. 1 minus 0.996 equals 0.004. So you take the square root of 0.004 and then do the reciprocal of that, and you should have gotten 15.8 for gamma. So now, part A. If you look at things from Earth's frame of reference, seen from Earth's frame, this time, the 0 subscript would be the muon's frame, and the delta T with no subscript would be Earth's frame. It's going to be the other way around in point B, or part B. That's why people sometimes confuse which frame is which. But the 2.2 microseconds, that's the lifetime in the muon's rest frame. So that goes in here. The Earth's frame is the frame of reference where the muons are moving. Okay, so that the time as seen from Earth is going to be this delta T. So we've got 15.8 times 2.2 millionths of a second. Gamma is a dimensionless number, by the way. It's going to be microseconds times a number with no unit gives you microseconds for the answer. So traveling at that speed, these particles that would decay in just a couple of microseconds, if they were sitting still, last for about 35 microseconds, which is enough time to cover the distance to sea level. Many of them have passed through my body since I started talking about this. They are, unlike some other forms of radiation, they are completely harmless. They interact with matter very poorly. That's why certain types of physics experiments are done in like old abandoned salt mines and places like that, is to shield the experiment from muons. Because, you know, you just put a couple inches of lead over your experiment, yeah, that'll stop gamma rays and things, but muons, they just go right through it. Half a mile of rock, no, that works a little better. Anyhow, part B. Now look at things from the muon's frame of reference. From the muon's frame, Lorentz-Fitzgerald contraction. This time, the Earth is the frame of reference with the 0 subscript, because when it says the muon was created 8 kilometers, 8,000 meters, I switched it over from, you don't have to, you could leave it in kilometers if you wanted to, but since it was going to be just a fraction of a kilometer for the answer, I switched it to meters. But the question doesn't say you have to. Anyhow, that 8,000 meters is what somebody standing on the earth would measure up to the altitude where these things are created. And so that's a distance in the Earth's rest frame. And what is that distance as seen from the muon's frame, the frame of reference where the Earth is moving? So this time the Earth gets the 0 subscript. If you get them mixed up, just keep in mind what's supposed to happen. When something is moving, it's supposed to get shortened. And if you've done a calculation where it looks like it gets bigger, go back and do it over because you've got them switched. Okay, the next thing it says there is momentum. If you start doing some calculations for things colliding with each other, momentum methods lend themselves very nicely to collisions. That's how you usually analyze a collision, as we saw earlier in the course. Well, it turns out that when things collide at very high speeds, the quantity m times v is not conserved. This idea is extremely upsetting to the average physicist. I mean, conservation of momentum is one of their most cherished ideas. Fortunately, all you have to do is make a minor adjustment in the definition of momentum in order to save it. Instead of momentum equals mass times velocity, momentum has to be redefined as gamma times m times v. If you do that, conservation of momentum is saved. It still works even when things collide at high speeds. And it reduces down to what I told you earlier for low speeds. Because remember I said a while ago that for people running around on a football field or throwing baseballs or something like that, gamma, for all practical purposes, is equal to 1. So gamma times m times v would be just m times v for two balls colliding on a pool table, because gamma is equal to 1. But at high speeds, it's necessary to introduce that factor of gamma. So looks like it's actually gamma. We're here. It's actually gamma times m times v. That's conserved in collisions. Now, this suggests adding a third thing to the list of quantities that are altered at high speeds. Time gets slowed down, length gets shortened, and in a sense, things behave like they're more massive, okay? So time, length, and they get heavier, well, except that they don't. Any kind of gravitational effects depend on the rest mass, okay? So there are actually different points of view on this. Some physicists would define the word mass a little differently than others would, but the most mainstream way of doing it anyhow, I guess the majority opinion, is to say that the word mass means the rest mass, okay? If you take something and sit it on a balance at the back of the physics lab here, that number you get off the balance is what's meant by the word mass. And, as it sits on the balance, it's at rest, right? So the rest mass. But from the point of view of how much inertia it has, things act like they get heavier. If you think that mass means, how hard is the baseball going to hit you? If how much of an impact is there going to be for something moving at a given speed? That depends on gamma times m rather than just m alone. So a baseball traveling close to the speed of light is going to hit you harder than Newtonian mechanics would say that it should. And so in that sense, things act like they're heavier when they get close to the speed of light. Mass has increased from m to gamma times m. So once you've got this expression for momentum, you can use that to calculate the amount of work needed to accelerate something from rest up to a speed v, which is another way of saying it's kinetic energy. How much work is a moving object capable of doing? How much kinetic energy does it have? It's just two ways of saying the same thing. And if you go through that calculation, the kinetic energy comes out equal to this. This expression here, kinetic energy equals 1/2 mv squared, one that you've used quite a few times by now. Close to the speed of light, that is wrong. This is one of the points where Newtonian mechanics breaks down if you're close to the speed of light. This is one of the ways that Newtonian mechanics is like talking about frictionless surfaces or ideal gases or something like that. This expression is simpler than figuring out kinetic energy from this. And at low speeds, it's going to give you the same answer, at least as long as you don't try and go to too many decimal places. But at close to the speed of light, it will be nothing like correct, okay? This can be derived from that under the assumption that the speed is much, much less than the speed of light. Just taking that and writing it another way, the speed of light squared is a common factor. So you can factor out the c squared like that, which if you reflect on it for a little while, makes kind of an interesting point. The way you convert units is by multiplying by some kind of conversion factor, okay? Centimeters times 2.54 gives you inches. Well, in the same way, kilograms times some number that's always the same, roughly 9 times 10 to the 16th, kilograms times that number gives you joules. Now, you can only convert units like that if it's between units of the same thing, okay? You can't convert from centimeters into liters by multiplying by some conversion factor, or you can't convert from centimeters into seconds by multiplying by some conversion factor like that. They're two different things. But kilograms and joules, the same number of kilograms always corresponds to the same number of joules. This suggests that kilograms and joules are just two different units for the same thing. And that's one way of leading into the idea of the equivalence of mass and energy. If you set an object in motion, the energy it gains is equal to, well, like I said, there's this whole issue about exactly what are you going to define the word mass to mean. But from the point of view of an object's inertia, anyhow, how hard it will hit you at a given speed. In that sense, the object gets heavier, and the amount of mass gained equals the amount of energy gained times some conversion factor, just like changing units. Kilograms times a constant equals joules. So a kilogram then is just another unit of energy. Mass and energy are equivalent, equals mc squared, like it says on all the physics t-shirts. Now here I was talking about kinetic energy in particular, but the same idea applies to any kind of energy. And there's some examples of that coming up as we go on through this. But first, the rest energy of an object is the energy that's equivalent to its rest mass. Okay, if you've got a baseball and it's just sitting on the table, its mass times c squared is the energy that's equivalent to its mass. This total energy when it's in motion, well, that would be the rest mass plus the kinetic energy. That's, you just, if you take this up here and you add mc squared to both sides, then the rest energy plus the kinetic energy is all the energy the baseball has. And that's equal to the gamma mc squared. This all just follows from what kinetic energy means. The energy something has when it's moving minus the energy it has when it's not moving equals the energy of its motion. Okay, that's what's going on with this. So the kinetic energy, well, just what I just said. If you throw the ball, it has more energy than when it's sitting still. The energy when it's moving minus the energy it has when it's not moving, that's its kinetic energy, and that's what's going on with this. And I guess I was actually a little off the bottom of the picture now that I glanced at the monitor, so time for another boost. Kinetic energy is the energy when it's moving minus the energy when it's not moving. A little note about units. This way. People who work in atomic physics are not actually in the habit of measuring energy in joules very often, for a couple of reasons. One of which is if you're talking about, electrons moving around inside atoms or something like that, a joule is a really large amount of energy when that's the thing you're talking about. I mean, a joule is a really small amount of energy if you're talking about a supertanker moving through the ocean at 12 knots. But for an electron, a joule is a huge amount of energy. So something smaller would be more convenient. Plus, this unit is defined in a way that makes it very convenient for the way that many of the experiments work. An electron volt is the amount of energy that an electron would gain as it moves through a potential difference of 1 volt is the idea. But all you have to know, and this is a conversion factor you can look up on the formula sheet along with all the other conversion factors. All you really need to know is that this is a unit of energy commonly used in atomic and nuclear physics. It's equal to this much of a joule. Or when things get a little on the energetic side, stick one of the metric prefixes on there, just like a megameter would be 1,000,000 meters. A mega electron volts is 1,000,000 electron volts. So time for you to try your hand at something. Now, I should probably throw you a hint for part A right now, because otherwise nobody's going to get it until I go over it. The hint is this. I have here the formula sheet, page 5. And there's this table down there where you can look up the speed of light and things like that. Notice the rest mass of the electron, what many people would simply call the mass of the electron, is given in kilograms, but next to it, MeVs over C squared. If an MeV is a unit of, million electron volts, if that's a unit of energy, and E equals mc squared, well, from E equals mc squared, M equals E over C squared. So a unit of energy divided by C squared would be a unit of mass. So the rest mass of the electron, if you take away the C squared, that would be the rest energy of the electron, which is exactly what part A is asking for, which I think I've just made part A really, really easy, hopefully. For part B, the total energy, well, you're given the speed of the thing. From that, you can calculate gamma, like I've already done it, or between us, you and I have done it a couple of times in this unit already. You might take a look at this once you've got a value for gamma. And then to get the kinetic energy, you might think about the one on the bottom here. And here's where you pause it and work on it yourself. And I'll go through here and erase the blackboard. Okay. The rest energy. So you look at the formula sheet where I was just showing you. The rest mass, M, 0.511 mega electron volts over C squared is the way it's labeled there. So you look that up in the formula sheet. E equals the rest energy equals mc squared. C squared over C squared cancels out, and you're left with E0 is 0.511 MeVs. How's the question phrased? It says, what's the rest energy in electron volts? The question specifically asked for electron volts rather than mega electron volts. So you just have to move the decimal 6 places. Okay, mega means 10 to the 6. 0.5 times 10 to the 6 is, well, I suppose you could just write it down that way, but yeah, your math teacher wouldn't have liked that very much. If you want the scientific notation in standard form, the coefficient should be between 1 and 10. A calculator will accept it if you don't do it that way, but really it looks better if you call it 5.11 times 10 to the 5th electron volts instead of 0.5 times 10 to the 6. Part B. As it says there, E total equals gamma times MC squared. Well, MC squared was the answer to part A. So what I have to do is I have to figure out gamma and then multiply it by the 5.11 times 10 to the fifth. So for the third or fourth time today, gamma is 1 over the square root of 1 minus, this time it's 0.8 C over C squared. And, oh, if you want to see the intermediate steps, C over C cancels out. .8 squared is 0.64. You subtract and you've got 0.36. The square root of 0.36 is 0.6. And the reciprocal of that is 1 point. Repeating 6, 1 2/3. So 1 2/3 times 5.11 times 10 to the fifth electron volts. .52. Part C asks for the kinetic energy of this electron. The energy due to its motion is equal to the energy it has when it's moving minus the energy when it's not moving. These would be the two previous answers, okay? The energy with the electron moving is the 8 point, that number up there. And the electron at rest has this much energy. So subtract, and it's 3.41 times 10 to the fifth electron volts. And I really should know it for extra emphasis. Just like I'm grading somebody's paper. Now, you know what? That's worth 4 exclamation points, I think. I invite you. This would be one of those optional problems for the student that I always sort of rolled my eyes when one of my professors said, "Oh, I'm leaving this as an optional exercise for the student. It's like, yeah, I've got quite a bit to do as it is. So in the unlikely event that you feel like exploring this for yourself, I invite you to look up the mass of the electron and multiply it by the speed squared, the square of the speed given in the question. And, you know, put it in this, and you'll find that is not the amount of kinetic energy that you get. Okay, as I mentioned earlier, this is a low speed approximation. It works very nicely for balls on a pool table or airplanes buzzing around an airport, but for something going 80% of the speed of light, it fails. Well, on the bottom of this page and continuing on to the next page, a few words about why no object can actually reach the speed of light. I've mentioned a couple times elementary particles moving at speeds very close to the speed of light, but you can never actually achieve the speed of light exactly. And you certainly never get to go any faster. So, you know, you watch some movie where the guys getting or the people getting the spaceship and they now passing light speed, you know, well, you know, it makes for a good movie. I've got nothing against movies that have, you know, like fairies and dragons and things like that in them also. That can be fun. But you need to realize that you are looking at a fairy tale, and for a not only a vehicle but anything, an electron, to move faster or even equal to the speed of light, yeah, that violates basic laws of nature. So you may or may not have noticed that as gamma approaches the speed, you know, as V approaches the speed of light, gamma becomes infinitely large, okay? If V was equal to C, then this factor over here, or this part over here, becomes equal to 1. 1 minus 1 equals 0, and you've got a 0 denominator. And of course, you just can't do that. But even if you're extremely close to the speed of light, which is mathematically allowable, you know, like what if you're 1 mile per hour less than the speed of light? Well, then this here will be almost 1, which means 1 minus almost 1 gives you a really small number for the denominator. Dividing by something really small gives you something really big. And if you get even closer to the speed of light, like, you know, you're 1 foot per second below the speed of light instead of 1 mile per hour, then the denominator gets even smaller and this gets even bigger. And if it's 1 inch per second less than the speed of light, then this gets really, really small, which means that, well, anyhow, the point is that as V approaches the speed of light, gamma approaches infinity. So as V approaches C, the amount of inertia that an object has becomes unlimited. And therefore, as you get close to the speed of light, no matter how large a force you apply, okay, no matter how much thrust you get from your engines, when you get close to the speed of light, that force becomes ineffective at causing further acceleration. In the sense of how much inertia the object has, more energy makes the thing get heavier, not faster. So giving a body kinetic energy is the same as giving it mass, okay? However you choose to define the word mass, energy has inertia. And, and so giving the object more kinetic energy makes it behave more sluggishly as you try to accelerate it further. So as it nears the, and I have to turn this over in mid-sentence. As it nears the speed of light, it gets too much inertia for further significant acceleration. More energy makes the particle heavier, not faster. And you see this in physics laboratories every day. A modern particle accelerator can get elementary particles, you know, protons or electrons or little ions or something like that. You can get them up to energies of trillions of electron volts in the current generation of particle accelerators. And you can get even higher energies than that from cosmic rays. And these things just inch up toward the speed of light, but they never reach it. Now, this is not to say that, you know, if you know Darth Vader is doing something bad in this star system over here that's 100 light years away, theoretically, if you could find some enormous energy source that could get a spaceship going very close to the speed of light, that's not to say that you can't hop in your spaceship, go over to that other star system that's 100 light years from Earth, take care of Darth Vader, then hop in your starship and come back. The problem is when you get back to Earth, it's 200 years after you left and nobody cares. They've never even heard of Darth Vader, most of them, okay? Time dilation. Well, for something like I just described, actually, you would need to get into the general theory of relativity because the spaceship has to accelerate to turn around and come back. But it's time dilation. In principle, you could go visit the Andromeda galaxy if you had a sufficient energy source to get you going that fast. The Andromeda galaxy is roughly 2 million light years from the Earth. You get back to the Earth and it's 4 million years after you left. And people really don't care. Anyhow, moving along, a good example of the equivalence of mass and energy is the binding energy of a nucleus. Binding energy means the energy needed to pull an atomic nucleus apart. A nucleus is a glob of protons and neutrons that are stuck together by the nuclear force that holds the whole thing together. And if you had small enough fingers to reach in there and start pulling out individual protons and neutrons, you would have to do work against the attractive force that holds the nucleus together. Okay, just like pulling two Legos apart, you have to exert some effort. You have to do work against friction. You would, pulling a nucleus apart, you have to do work against it's called the strong force, the force that holds the nucleus together. So adding energy to those protons and neutrons as you do work on them, pulling them out of there, adding energy to them makes them heavier, okay? There are ways of measuring the mass of an atomic nucleus that give you many decimal places. And so if you measure the mass of the nucleus with it all put together, and then you add up the masses of the individual protons and neutrons that it's made of, you will find that the individual particles add up to more mass than the mass of that nucleus. And the difference is the amount of energy you had to provide to pull the thing apart. That energy weighs something, okay? So by the mass apart, I mean, the simplest nucleus would be, that you could talk about would be a nucleus of, well, now let's do something a little more familiar. A helium nucleus, 2 protons, 2 neutrons, okay? If you add up the mass of individual protons and neutrons, 2 of each, it's a little bit more than the mass of the helium nucleus, which is all 4 of those particles stuck together. The difference between those times c squared is the amount of energy you would have to provide to pull the nucleus apart. It's so-called binding energy. So I'm going to run through an example, and then you run through a couple of examples, and then that'll be all there is to section 14. This one that I'm going to do is not exactly the binding energy of a nucleus. You've got one of those coming up that you'll work on yourself a little further down the page here. This one, it's another example of mass and energy being equivalent. This deals with an elementary particle called a pion. A lot of elementary particles have been named after Greek letters. So the rest mass of a pion in kilograms is this. The great majority of elementary particles are unstable. Protons and electrons are the exceptions, but most of these things have half-lives that are small fractions of a second, and that includes this thing. So the pion, after you've made one in your particle accelerator, will decay into a muon and an antineutrino, and probably some unfamiliar names. If anybody's interested, call me up. We could have a long conversation about this stuff, but I don't want to go off on a long tangent about what all these different particles are. Just this particle decays into that particle and this particle. So it can be shown from conservation of momentum that a little over 12% of the energy produced in this process becomes the kinetic energy of the muon, the remainder becoming the energy of the antineutrino. So part A, find the kinetic energy of the muon, and part B, how fast is it going? So basically, before I write out the details, the basic idea here is that you might notice the particle that this thing turns into is significantly lighter. Where did that mass go? Well, a neutrino, by the way, is, well, it's not exactly a massless particle like a photon is, but it's the next best thing. The masses of neutrinos are so small that actually, even today, physicists would really like to know exactly what they are. I'm sure they'll figure out a way to measure it sometime in the next few decades. But the rest energy of a neutrino is a fraction of an electron volt, as opposed to an electron, which was almost 500,000 electron volts. An electron is a lightweight particle compared to most of the others. So to an excellent approximation, at least, a neutrino has no rest mass. So it's not like the missing mass went into the neutrino. The mass that disappeared got turned into energy, some of it being the kinetic energy of the pion, and the rest of it becoming the energy carried by the neutrino. So the plan of attack here is I just subtract these two numbers to see how much mass disappeared. 12.15% of that became the kinetic energy of the pion, and you do E equals mc squared with that amount of mass, and that's the answer for part A. So details like this. Mass that disappears is the energy produced. So how much mass disappeared? Multiply that by c squared. By the way, this is one time when we will not be working to, maybe get to the answer and round it off to 3 significant digits, and that's fine. But the numbers along the way, if you round them off to 3 significant digits, it will create significant problems. Write down all the digits that the question gave you, which in this case was 5 of them. Didn't really leave myself much space. I'll kind of squeeze it in here. That's speed of light is actually just a hair underneath 3 times 10 to the 8th. It rounds off to 3.00. You need more digits here because you're going to subtract, and if the numbers are close to each other. Anyhow, this comes out 0.43. Because the mass was in kilograms and the speed of light was in meters per second, the energy will come out in joules. A joule is a kilogram meter squared per second squared. So that's the amount of energy created as, conservation of energy has to include mass. You have to think of mass as a type of energy. Mass by itself need not be conserved. Energy in the traditional sense from the 19th century doesn't have to be conserved because it can be turned into mass or out of mass, okay? But you put them together, if you think of, anyhow, basically what's happening here is some energy is being converted from one form into another. What used to be some mass has been converted into kinetic energy. 12.15% of which goes to the pion that we're interested in. So to calculate 12.5% of that, you multiply by 0.1215 and 6.60 10 to the negative 13th joules. I should probably write down where I got that. And that's the answer to part A. That's the kinetic energy of the muon in joules, which if you wanted electron volts, you could convert it, but the question didn't specify what answer to have it in. Part B, how fast is it going? What's the speed of the muon? Well, once again, it's going too fast to get away with that, okay? Rather, what we're going to have to do is get a value for gamma and get V out of that. Gotta make some more space to write over here. Back to that idea that kinetic energy is equal to the energy something has when it's moving minus the energy it has when it's not moving. The energy it has when it's moving is gamma times mc squared. Its rest energy is mc squared without the gamma. And as I said a moment ago, the way we're going to get the speed of this particle is by calculating gamma. And then, well, once you know gamma, you could just say gamma equals 1 over the square root of 1 minus v over c squared and do several lines of algebra and solve for v out of that. But it happens that your friendly neighborhood physics teacher did those several lines of algebra for you. And this is the formula sheet, the section of the formula sheet where section 14 is. And if I can, it's a little fuzzy looking, but right there by my finger, see for over here, there's the equation that I've been using for gamma. I take that, I do some algebra on it and solve it for V. So once we have a value for gamma, you can just drop it in there and that saves you doing 3 or 4 lines of algebra because I'm just that kind of guy. Anyhow. I could drop the numbers into it at any point here, but it's one of these things where I want to do the algebra first. You don't have to. It's just what I did. So I take this, I do a little algebra to solve it for gamma, and I'll drop the numbers in now. Like it's just, they're kind of big, cumbersome numbers that I didn't feel like writing over and over again. Just these few letters seemed like it was easier, so I thought I would do the algebra first. But now I've got 1 plus, for the kinetic energy, that was the answer to part A. 6.6 10 to the negative 13 joules. MC squared. The question gave us the mass of the, it's a pion, wasn't it? Or no, it's after it's decayed, it's a muon, right? So the mass of the muon, 1.8835 10 to the negative 28 kilograms. That's M, and then C squared. If you want to be really careful with it, 2.998 times 10 to the 8, but it rounds off to 3.00. Anyhow, that's going to be copy the 1. This divided by those is 0.0390. So gamma 1.039. So from where I was just pointing out on the formula sheet, it says the speed of the particle equals the speed of light. And that's so you get that from the formula sheet. You fill in the value that I just calculated back here. Run through your calculator, 0.271. Or you can fill in the meters per second for the speed of light if you'd rather have that in meters per second. But I think saying 27% of the speed of light is probably more meaningful to most people than whatever that many meters per second is. Okay, so a couple for you. Let me see if there's anything I should say about these that would be helpful before I completely turn you loose on them. For one thing, it would be helpful if you could actually see the question. In number 3, you are given some numbers about a nucleus of heavy hydrogen, what those of us in the trade call a deuteron, okay? Most hydrogen atoms have a nucleus that's just a lonely little proton. But occasionally you find a hydrogen atom where the proton has a friend. The nucleus consists of a proton and a neutron. So that would be the simplest nucleus where you can have this conversation about a binding energy. Quite often in atomic work, we work in atomic mass units instead of kilograms. It's a unit that's approximately, not exactly, but approximately equal to the mass of a proton or the mass of a neutron. Neutrons are actually a little heavier than protons, but in those units, this is the mass of a proton. This is the mass of a neutron. And this is the mass of the nucleus formed by sticking the two of them together. So we want the binding energy. That's a matter of putting numbers into this equation with the box around it up here. The main thing is you'll have to convert from atomic mass units into kilograms. My advice is to do all of the, the adding and subtracting. Do the arithmetic first while it's in atomic mass units. I think it's a little more convenient that way, although it won't actually affect the answer. But before you, it's all fuzzed up now. Before you go multiplying by the speed of light squared, you'll have to convert from atomic mass units into kilograms, and then that'll give it to you in joules. Once you've got the binding energy in joules, you convert it into electron volts. I think it was on the previous page of the notes, the conversion factor was there, or you can find it on the last page of the formula sheet. It's just a unit conversion, similar to many others we've done. So see how that works out for you. Pause it here. Number 3. Okay, binding energy is the mass with the nucleus apart minus the mass it has when it's together. That difference times c squared. What I mean by the mass apart is add up the individual masses of the particles. If you just weigh them in isolation, what do you get for the mass of a proton? What do you get for the mass of a neutron? And those two numbers are both given in the question. If you add them together, you would get 2.016490 of an atomic mass unit. You let those two particles stick together, and now you've got a nucleus of heavy hydrogen, and its mass is 2.014102. So the difference .002388 of an atomic mass unit. But like I said at the beginning, a joule is a kilogram meters squared per second squared, not an atomic mass unit times meters squared per second squared. So you have to convert that into, oh, it's not a mu, it's a u. The conversion factor is given right in the question. Probably ought to shift the camera over a little bit. You want atomic mass units on the bottom so that they'll cancel out. And it says in the question that one atomic mass unit is 1.66 times 10 to the negative 27th of a kilogram. So we've got 3.964 times 10 to the negative 30th. For the amount of mass that's disappeared. Well, disappeared if you let them come together, appears if you take it apart, I guess. Depends on which way you want to look at it. And that mass times c squared equals the binding energy. .56. .56 times 10 to the negative 13 joules. It wants the binding energy in both joules and electron volts. Electron volts is just a unit conversion. We want joules on the bottom, so it'll cancel out. 1.60 times 10 to the negative 19th of a joule equals 1 electron volt. And so joules over joules cancels. Get your calculator, you divide those numbers. 2.22 2.2 million electron volts is the binding energy. That's how much energy you would have to supply to pull it apart. That's how much heavier things are when you take them, you know, when you weigh them separately. One more. This is about the Lorentz-Fitzgerald contraction. What is the speed of a meter stick, which is only 80 centimeters long? So you go back to get the expression for the Lorentz-Fitzgerald contraction. There's always somebody, when we're doing this in class, who's sitting there looking puzzled at their paper going, how do I know the rest length? And I just say to them, it's a meter stick. And they go, oh, yeah, duh. So you know the rest length is a meter. You know that at whatever speed it's going, it's contracted down to being only that long. And from that you can get gamma, and then you can finish it off the same way I finished off this one with the mu on a little while ago. You can get that off the formula sheet. And pause it here while I erase the blackboard and work on that one. sheet of paper. You know, gamma. You put the 1.25 in there. And comes out even, actually, 0.6 of the speed of light, 60%. Or in meters per second, 1.80 times 10 to the 8th meters per second. And that gets us to the end of the new material. There's a review sheet for the final exam, and then after that, everybody gets a few weeks off. If you're coming back in the spring for Physics 122, which of course I highly recommend, there's one slight difference. I mean, it's the same time slot and everything, but unlike the recordings from last fall, which I deleted at the end of the semester because, oh, that course is over, I won't need those anymore. By the time we got to the end of the spring semester, I had an entirely different outlook on that. And so actually, at least for the lecture part of the course, your instructor for Physics 122 won't be present day me, it'll be year ago me. But hopefully we'll see each other during the lab period. Who knows what the virus will be doing by then. But I know many of you prefer the face-to-face version, you know, labs, and that's the way I'd rather do it myself if we can get away with it. So meanwhile, enjoy the break.